Hi, this is Professor Verkler from the University of Utah, and this is lecture 4-6 for ECE 1220. Today we are going to learn about drawing finite state machine diagrams for sequential logic. We'll practice drawing timing diagrams, and then we'll learn how to create a circuit from a finite state machine diagram. And I think that last part will be in a second video. So, here's a conceptual overview. We've previously learned about combinational logic, which is where we create networks of and, or, and not gates based on a set of inputs, and then we create the desired output. And then we talked last class about adding storage elements to store previous inputs and allow our outputs to be dependent on that. And we created storage elements using latches and flip-flops. And the flip-flops were run by a clock, which was a timing signal, a digital signal that goes periodically up and down, up and down, up and down, and runs our whole system. So we've been talking about inputs and outputs for a while with our combinational logic. The new thing we're adding with the memory is what's called states. So a state is something we can be in depending on what the previous inputs were. So I'm trying to think of a good example of that. Maybe you want to know if we had previously received money in the vending machine, right? So we need to know like how much money we had already gotten. And so our state is how much money has already been put in to know when we have had enough money put in. And we will actually do a finite state machine diagram for that in a few slides. Okay, so let's talk about drawing finite state machine diagrams. So this is a Mealy machine, finite state machine. And so I want to just point that out because up here it says Mealy machine. If you're looking on the internet to learn about this more, there are two types of machines, Moore machines and Mealy machines. So if you watch a video about Moore machines, you're going to get very confused because Moore machines are drawn differently. We're just learning Mealy machines in this class. So we have circles to represent the state we're currently in, the memory state, and then we have arrows to represent how we transition between those states. And the arrow will tell us what input will cause us to transition to that other state, and it'll also tell us what output we should give in that case. And the important thing to remember when drawing these diagrams is that you have to make sure that we have a transition, right, a path or a transition for every possible input. Otherwise, I could get stuck in a state. Okay, so let's do an example. Here's a stoplight. So if we're in red, right, that's kind of our starting spot for safety. Then at some point the light will turn green. And then after that the light needs to turn yellow. And then the light turns red. Now notice those arrows kind of match up with what we drew up here with this finite state machine. It's just kind of rotated. So let us draw a finite state machine for the stoplight. And we can imagine we have some kind of timer, and maybe the timer is t equals 1, means it's counting down. And t equals 0 means that we are ready to switch colors. And we won't worry about the details of how the timer is being run. That's kind of something we can think about later. Okay, so I'll make my states red, yellow, or maybe you call it orange. I don't know, I call it orange. My husband and I argue about this all the time. And green. So red to green, green to yellow, yellow to red. And we will make this transition when t equals 0. We're ready to switch colors. T equals 0. T equals 0. What do we do if the timer is still counting down? Well, we'd want to stay in that state and keep outputting the same color. And so then what's the output? That'll come after the slash. So the output in this case is we're heading to green. So green should be turned on. Over here, if we're staying in this state, green should be turned on. Over here, we're switching to yellow, so yellow should be turned on. We'll let the logical one represent that. Over here, red should be turned on. Over here, yellow should stay on. And over here, red should stay on. Now, maybe you also want to send out a signal telling the timer to start. Again, I'm not worrying about the details of that in this simplified example. And then also, to fully represent your outputs, it might be good to say red equals 0 here, for example, and green equals 0. Specify what all the outputs are going to be. I had just kind of simplified it here and only wrote whichever ones would be 1, assuming all others would be 0. But for a fully complete diagram, you might want to specify very clearly whether it's a 0 or 1 for every output. Okay, let's do another example, that vending machine now. So I've simplified down a vending machine so that we can draw a beginning finite state machine diagram for it. So it only has one type of snack, and the snacks cost $1, and our machine just takes quarters and dollar bills. So a quarter is the input of the binary number 0, 1, and a dollar bill is an input 1, 0. And then an output of 1 means release the snack, 0 means don't release snack. So now you might be wondering, like, oh, what happens if there's no quarter or dollar put in? So if you wanted, you could have like a 0, 0 input into this finite state machine. There's also ways we can handle, like put an and before the clock. And so we have to have both a button pushed and the clock high to actually enable our whole system. And so there are details like that we can kind of just not worry about this and assume our system's only going to run when an input occurs. And we'll talk more about how to implement that clock in the next lecture. Okay, so assuming that we only go and look at this diagram whenever money is input, so we don't have a no input state, well, we're going to start by keeping track of how much money is in the machine. So we start with no money. Then we could put in a quarter. So that's a 0, 1. We don't want to give out a snack yet because we've only gotten a quarter. So we put an output of 0. And now we're at the 25-cent state. Then maybe we put in another quarter. Still don't want to give them a snack yet because they've only put in 50 cents. Then we could put in another quarter. Still don't want to give them a snack because they've only put in 75 cents. And then finally, if they put in another quarter, we've gotten $1 worth, and we'll release a snack. So again, this finite state machine is just keeping track of whether we've gotten enough money and whether we can release the snack. The details around like how long this snack release takes will be worked out in logic outside of the scope of this finite state machine. And so it can go to a latch, run the whole mechanism to release the snack, and then maybe disable this whole logic circuit until it's done, and then we're back in the 0 state. So again, we're not going to worry too much about those details. Okay, so now what if we got $1, right? If we got $1, we just immediately, right, take the $1 and give them a snack. Now what happens if we're in the 25-cent state and we get $1? Well, in that case, we will give them a snack and no change. Same thing with 50 cents. They could put in $1, they've overpaid, but they'll still get a snack. And then we're ready to start counting money again for a new snack. And same thing with this final arrow here. If they put in $1, we'll give them a snack, and they just don't get change. Now notice we have 2 arrows heading from the 75 cents to the 0 cent, and it's 2 different inputs here. So what I would probably do is I just simplify this to a single arrow and say I would take 0, 1 or 1, 0 in either case. I'll give out a snack and go back to the 0 cent state. And that's the end of our practice of finite state machine diagrams. Go ahead and try the worksheet now, and then come back and watch the next video on how to create circuits from the finite state machine.